Hello and Assalamu alaikum. My name is Ahmad Abrayu and we are from group 15. So our title is Differential Equation in Academic Disciplines. So our group members consist of Muhammad Farhan bin Waziri, Ahmad Abra bin Ayub, and Gua Chi King. So without further, let's start it.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Farhan bin Rozili and my matrix number is 208240, and good evening to everyone. So now for the team assignment 1, I will present the objective first. The objective of the assignment 1 is to find the uses of the differential equation in many aspects. This because the differential equation can be applied in any field of study. In general, any type of physical quantities such as temperature, pressure, displacement, velocity, stress, strain, current, voltage, or concentration of pollutant can be measured by using the differential equation. Next, the objective is to investigate the application of the differential equation in specific field of study. This is because the result of the application differential equation formula is different from one another. And lastly, the objective is to explain the principle of the differential equation. The detail of the explanation towards the differential equation could result in improvement of the level of the understanding of a student. So that's all from me. Thank you.
So for the introduction of the differential equations, it is a differential equation is a mathematical equation that connects one or more functions and their derivative. First, in applications, functions are used to represent physical quantities. Derivatives are used to describe their rates of change, and the differential equation is used to define a relation between them. Differential equations play an important role in many areas, including engineering, physics, economics, and biology, because such relations are widespread. The studies of differential equations primarily entail looking at their solution, the set of functions that satisfy each question, as well as their priorities. Only the most basic differential equations can be solved using explicit formulas. Nevertheless, many features of solution to a differential equation can be known without computing them precisely. So, as I know that differential equations is we are familiar with it. It's common for us because we have basic part. Even before the degree, we know the differential equations. If I'm not mistaken, we learn it when we are in high school. So it's not a new thing for students in degree. So differential equation first come in existence with invention of calculus by Newton and Leibniz in chapter 2 of his 1671 work work Motordus Fluxionum at Serenum. Yeah, that's just the name of the book. And the order of the differential equation is the order of equation's highest order derivative. Here are some instances of differential equation in the various order. So as we all know that differential equation has many orders, like first order differential equation, second order differential equation, and the first order is dy over dx, while the second order is d squared y over dx squared. And it depends on us. We want to differentiate the equation against x or against y.
Okay, so now I will present to you for the principle of the equation for the team assignment 1. So firstly, the principle of the equation itself can be written in different form. You can see in the on the left side of view, in the left side of slide, the below the picture shows that the variation of the uh, differential equation form. So the dx is meant by the indefinitely small change in x. The dy is mean the indefinitely small change in y, and the dt is the indefinitely small change in the time taken, which is the t. So on the right side of the slide, you can see that the example of the solution, which is the integral parts in the differential equation. So we have to integrate both the unknown and the numbers by increasing one by increasing by one. So you will see the final answer with the plus of k, because we don't know the constant of it. So next, the differential equation also comes with different form, which is you can see on the slide. It comes with a heterogeneous, homogeneous second order, and other than that. So that's all from me. Thank you.
So let's move to the application of differential equations in terminal velocity. In physics, supposedly in terminal velocity, using Newton's law, we model a mass m falling under gravity but with air resistance. We assume that the force of air resistance is proportional to the speed of the mass and opposes the direction of motion. We define the x to the point in the upward direction opposite the force of the gravity. So we know that anything that falls from the only gravity factors is forced by the gravity. And we know that the higher the weight, the more the more it the more it can reach certain amounts of velocity, which the resistance of air, of course. But without the resistance of air, everything fall with the same speed. Near the surface of Earth, the force of gravity is approximately constant and is given by negative mg, which is g equal to 9.8 meter over second squared, the usual gravitational equation. So here we have the gravity force, which is 9.8 meter over second squared. So here it write negative mg because the gravity is toward the down direction or toward the negative y directions. So we can assume that 9.8 is a negative 9.8 meter over second squared. The force of air resistance is modeled by negative kV. V is vertical velocity of the mass and the k is positive constants. So here we have the equations. M d over v over dt equal to negative mg minus kv. And here we got the m dv over dt. Here actually is mv, which is our momentum. So mv, when we differentiate v over t, we will get dv over dt, which is velocity differentiate against time, and equal to negative mv over kv, which is the our formula. So next, let's look for the terminal velocity. V infinity of the mass is defined as the asymptotic velocity after the air resistance balances the gravitational force. When the mass is at terminal velocity, dv over dt is equal to 0, which is when the terminal velocity dv over dt equal to 0. This is because v infinity equal to negative mg over k, and k is our constant. So when we differentiate when we differentiate velocity against time, we will get 0. The approach to the terminal velocity of a mass initially at rest is obtained by solving uh, 8.1 with initial condition v not equal to 0. The equation is linear and the standard form is dv over dt plus k over m times v equal to negative v. So that the integrating factor is, we can look here that the third formula, which is vt equal to epsilon to the power of kt over m times negative v times dt. And the solution to the function is negative mg over k times with the 1 minus epsilon to the power of kt over m. So that's the solution of the equation that we have. upheavals. So that's all for me, and let's move to the other person.
Okay, so now my presentation for the team assignment 1 will be for the part of the application in the glaciology. So as you can see, in the glaciology, the differential equation can be used to calculate the irregular shape of the graph, which is that can be obtained from the ice crystal plate or the ice crystal block itself. The isoparametric element and the numerical integration for the glacier. The majority of this is because the majority of the glacial structure are irregular in shape, with some having extremely intricate boundary shapes. Although the employment of the triangular element may always suit in difficult borders, the element position is generally low. So one of the most frequent technique to dealing with irregular boundary shape with improvement precision is an analysis is the employment of the high order element, with the isoparametric formulation being the most widely employed at the moment. So by using this formula, we can change the irregular shapes of the plate into uh, form into the regular shape of the plane, which is you can see the on the left side is the irregular shapes, on the right side is the regular shapes. So this is for the application. So thank you.
Hello, my name is Guo Jiaqing. For the differential equation application, my topic is LR and CR circuit analysis. This is contents. The part 1 is for introduction, and the part 2 is the analysis. Okay, for part 1, introduction. The application deals with analysis of circuit by using linear differential equation of first order. For a simple electric device, which there are at least one closed path for current to flow, is called electric current. There is the table for the element symbols: charge Q, current I, resistance, inductance, capacitance, and voltage. These are some basic laws for the electric circuits, like I equal dq over dt, the voltage drop across resistance, and voltage drop across inductance and the capacitance. There are two laws, the Kirchhoff's laws and the current laws. And there are two equations for the two kind of series circuit. Okay, next, for part 2, and for analysis, for the LR circuit, the switch is closed at time x0, and then to find the voltage across the resistor and the inductor. These are some basic laws, resistance and inductance. From Kirchhoff's laws, which is first order linear differential equation, we can get the general solution of I. For K as open circuit, I equals 0, we can get K. So because the V equal IR, we know I, so can get V. So at different time, we can get different value of I, also different VL and VR. Next, for CR circuit, there are also some of the basic laws, resistance and capacitance. From Kirchhoff laws, we can get this formula. When V0 equals 0, the differential equation of above circuit is like this. Then the integrating, we can get equation 1 at t equals 0, at t equals 0. Therefore, A equal log Q at 0. From 1, we can get the formula of V. So if we know the value of inductance or capacitance and resistance, we can use the first order differential equation in LR and CR circuit. we can find the current and the voltage in the circuit. Okay, for conclusion, we show about the principle of differential equations and their applications in glaciologies and circuit analysis. We can see the differential equation play a major role in application of science and engineering. It is very useful, and in wide variety of engineering applications, some engineering problem can be better solved. Okay, that's all. Thanks for watching.